If I look at the common operational modes in conventional TEM, you have the incident beam, and after the interaction with the specimen, you have the direct beam or the electron beam which is scattered at small angles. Typically, when your angle of scattering is satisfied by the Bragg condition, which is dependent on the crystallinity of the specimen, by either choosing the beams in and around the central beam or the direct beam, you can improve the contrast by inserting a diaphragm or the objective aperture, and by choosing the beam that is deviated at a specific angle of scatter as a consequence of the change in the diffraction conditions. This is actually a weaker beam than the central beam. So, this is called as weak beam diffraction conditions, which is then used to image and obtain what is called as a dark field image. So, here is an example of a specimen which is being recorded by allowing all the forward scattered electrons. In this case, if I now put in an aperture and allow only the central spots which are highlighted here, in fact, some of these spots are missing in this, my contrast actually improves slightly, and if I use an even smaller aperture, my contrast changes. Now remember, the resolution is again dependent on the spatial frequencies that I am allowing at the back focal plane. So, you are actually gaining the contrast. If I look at the histograms across these three features on this image, the difference between the brightest and the darkest regions is prominently more here than here. The slope is slightly changing than over here. So, you improve the contrast, but you also lower the resolution a bit. So, once you orient a specimen in the zone axis and you want to obtain high resolution imaging, you do not want to use any of the apertures to block the higher order frequencies to obtain a very good high resolution image. But when my intention is to image defects or to improve the contrast of the features that I want to see, then I intentionally use an aperture, and this is called as switching between the bright field and dark field images. The image shown on left is a bright field image from precipitates which are on the surface of an aluminum sample, and the image on right is by highlighting one of the weaker beams or the diffracted beams, and you can see the defects here and the bend contours more prominent. In fact, these are kind of the fringes that are caused as a consequence of variations in the diffraction conditions here within the specimen. So, bright field and dark field imaging is the most basic conventional imaging that you see in any transmission electron microscope, and this is the most used technique. And the primary mechanism of the contrast that you get in bright field and dark field imaging is due to the amplitude contrast, which in turn depends on the mass thickness and the diffraction contrast. Then we mentioned that when the parallel electron beams that are passing through a specimen go through the objective lens, they all form an array of spots at the back focal plane, and here is an array of spots that you can see from a crystalline material, a single crystal which is oriented along a crystallographic zone axis, and you can see that the intensity of the central bright spot is the highest, whereas the intensity dies down as I go farther away from the central beam. This is also what you see from an aperture, because you are using the illumination by using circular apertures which are restricting the path of the electron beam. The intensity naturally dies out as you go farther away from the central beam, and by orienting the specimen in specific zone axis conditions, I will not go into the details of zone axis orienting the specimen. We have seen the demonstration of these, and we have also seen some basics on crystallography of how the indexing of these diffraction patterns is done and how the orientation is done. Let us try to understand how these diffraction patterns are obtained in a TEM. So, if I look at this reference image again, where I see the microscope column and the schematic of the column, when parallel electron beam which is illuminating the specimen is imaged such that the specimen is also oriented along the crystallographic zone axis. That means if here is my unit cell within a crystalline specimen that is being imaged, if I orient the grains or the crystal in a direction such that one of the crystallographic planes is actually parallel to the electron beam, in this condition I am actually satisfying the Bragg's law. For the electron beams in the microscope, the angle of scattering is extremely small, of the order of 10 to 20 milliradians, or typically less than 3 degrees. So, as a consequence, all my planes which are oriented parallel to the electron beam would satisfy my Bragg diffraction condition, and when parallel beams go through an objective lens, they all converge at the back focal plane. Now, when I use the back focal plane as the object plane for the illumination lenses, I record the diffraction pattern. When I use the image plane of the objective lens as the object for the illumination lenses, what I record is the image. And we also established some time ago that this periodicity which is observed at the back focal plane can be related to the information within a specimen or the periodicity within a specimen through the Fourier transform, and the information I record from the image plane is an inverse Fourier transform of the information at the back focal plane. So, this is what happens in an electron diffraction pattern, and if I look at an electron diffraction pattern, the distances in diffraction pattern correspond to the angles of scatter. The most intense beam is at the center, and the scattering intensity decreases with increasing angle of scatter. The intensity varies strongly within the specimen, and there are specific methodologies with which I can start indexing these reciprocal lattice vectors, and from this I get the crystallographic information on the specimen. When I talk about solving the crystal structure and obtaining crystallographic information, I would say transmission electron microscope is extremely important to understand the symmetry, the positions of the atom and the crystal structure information, but it is a very localized technique. Often complementing this with an X-ray diffraction study gives you the complete information on crystallography from a material. So, when I define the crystal structure problem for any unknown material, you have to determine 3 parameters. Primarily, you have to determine the cell parameters which give you the lattice spacings. That is, when you define the Bravais lattice, you define the unit cell vectors in A, B and C directions. That is what you obtain from spot diffraction pattern when you are illuminating in a parallel beam mode. Then when I converge the beam and I record sort of disk patterns, I get the information on the symmetry from an electron diffraction pattern, and this is often recorded as what is called as a convergent beam electron diffraction. In this course, we only focused primarily on the spot patterns or obtaining electron diffraction patterns with parallel illumination. The determination of space groups and understanding convergent beam electron diffraction pattern is an advanced module, and once you are conversant and familiar with conventional diffraction and imaging, this becomes a natural next step and you can always take that leap. And next, the third important parameter is understanding where my atoms are sitting within a crystalline unit cell. Unless you've determined all 3 of these parameters together, you would not have solved a crystal structure. So, I'll just recollect how we've demonstrated that you can use simple tilting and parallel illumination in a basic conventional TEM to get the crystal structure information from a specimen. If you have a specimen which is oriented in this kind of a condition, and let us say there is a set of planes which are satisfying this parallel illumination with the electron beam, these planes give me some kind of diffraction pattern which is corresponding to this distance is here. So, if I call this as G1, so if I call this as D1, the reciprocal vector G1 corresponds to this distance, and this distance you see here now corresponds to this distance. In fact, this separation here is larger and this separation is actually smaller. So, you can say that this is G1 now and this is G2, or this can be D2, where G2 and G1 correspond to the reciprocal lattice vectors of these planes D1 and D2. If I now use one of the crystallographic axis as constant and I now tilt the specimen in this direction, I obtain the planes with varying G1 and this G2 remains constant, and with these variations, whatever projections I record, I can overlay them over each other and measure them and plot them on a kind of a graph paper and see with how much angle of deviation, how these diffraction spots are changing, and I can construct the projection of a reciprocal unit cell. So, this helps you determine the unit cell parameters very accurately, and once you know this, you can also get information on the symmetry either by corresponding X-ray diffraction pattern and by using Rietveld refinement methods, or by using convergent beam electron diffraction techniques and determine the symmetry, and then you would have solved the crystal structure to an extent. And then once you determine the space group through focus exit wave reconstruction imaging by high resolution electron microscopy, you can completely solve the crystal structure. So, at this point we will now move into the next methodology of imaging that we learned, which is high resolution imaging in TEM. So, if you look at an example high resolution micrograph from an uncorrected microscope, what you see here is a periodic pattern. Remember, this is not an image of the atoms, but it is an image of the atomic columns, and this is a high resolution image of the lattice fringes. Do not assume that these are actually individual atoms, but these are atom columns, or this is called as lattice fringes, and the periodicity you see here is a consequence of the periodic arrangement of atoms within a crystalline lattice. And if you consider each of the atomic columns are actually acting as sources to deviate my electron beam, and if I think of them as periodic sources arranged in a periodic manner, what I record here is sort of an interference pattern. I am overly simplifying this concept, but let us understand how high resolution imaging is done. So, primarily you have to check the diffraction pattern and orient the crystal into the zone axis. We discussed this in the demonstration sessions, and once you orient it into the crystallographic zone axis and do all the primary corrections, you can then start imaging and get information on the high resolution from that particular material. So, where do we start this? If you think of an isolated atom, the atom actually has an inherent potential associated with it. So, as the electron wave travels across the distance of the atom, it accumulates a certain phase, and this actually, if you compare it with the refractive index for light, you can substitute the refractive index with the phase modulation or the phase shift that is caused by an isolated atom, and what you then get is actually called as the projected potential. So, the phase modulation by an isolated atom to the charged electron is what causes the deviation of the electron beams, and from an isolated atom you can understand the phase shift is written in terms of the projected potential of an atom. Now, when I take this and extend it and build it to a crystalline sample, you can start with the simplest case where you have two simple atoms, and when you superposition these exit waves from these two, the contrast then depends on the atomic separation. This can be bridged with the classical Young's double slit experiment that you learnt, and the spatial frequencies are transferred by the lens. This also directly connects to your electron diffraction theory. If I consider the exit wave as an expansion like this, when I write a polynomial expansion for the exit wave in terms of the phase, this is actually a complex number which can be expanded. If you take what is called as the phase object approximation, in understanding the contrast variations in high resolution electron microscopy, a concept called as phase object approximation has been introduced. So, the electron wave that interacts with the specimen modulates the phase of the incoming electron beam, and in terms of the spatial positions of the atoms that are sitting within a crystal, you are varying the electron phase, and you can relate this phase to the potential associated with the positions of the atoms which are sitting in 2 dimensions. The third dimension of the thickness has been ignored in this particular equation that is shown here. When you take really thin objects, you can always use this kind of an approximation, and this is called as a weak phase object approximation. And when I look at the Fourier transform or the Fourier space of the information that is recorded at the back focal plane, you can write it in terms of the reciprocal lattice vectors as this. So, the interference of 2 atoms, this can be expanded further, and you build the concept of projected potential and modulation of this projected potential by the electron lenses, and as a result you get the high resolution phase contrast images. So, where does this contrast come from? The objective lens introduces a phase shift, and this depends on the spatial frequency, that is what we saw here. So, if I have an objective lens like this, the change in the focus can introduce some change in the frequency, and the positions of the atoms can also introduce the change in the phase. So, what I then get is, with a lens there is something called as the aberration function. So, the phase change just by a lens alone without introducing a periodic crystalline sample can be expressed in terms of an expression like this. So, this chi is called as your aberration phase function. It is actually a complex number, and u and v are the spatial frequencies, and the phase modulation can be written in terms of this aberration function. So, if I look at how the phase shift happens, it is given by this equation, and if I look at the real part of this expression, and when you do the polynomial expansion, you can take the real part as almost equivalent to 1. So, there is hardly any amplitude change as a consequence of the constant phase object, but when you look at the reciprocal part, when you look at the imaginary part, which is the sinusoidal of chi of uv, this gives me what is called as the contrast transfer function. So, if I use this expression in this kind of an exponential term and look at the complex function, you can think of lens as a spatial frequency dependent phase plate, and it strongly depends on the spherical aberration, the defocus, and the electron wavelength. Now, this information from a lens convoluted with the projected potential from the crystalline sample is what is recorded in an image in a high resolution micrograph. So, let us look at this contrast transfer function and recollect this. If you take the aberration function and you take the differential of it and look where it reaches a maxima, at a negative defocus you can counter the spherical aberration and you can get sort of a maximum intensity, and this is called as the Scherzer defocus. And when I look at the phase contrast that is obtained from these kind of images, this is analogous to the Zernicke phase contrast in optical microscopy. The sinusoidal part of the contrast transfer function of the lens transfer function appears like this, and this point of intersection is what is called as your point resolution, and as you go farther away these frequencies get damped, and the end of where these frequencies are completely damped, that is called as the information limit. And by changing the defocus and also depending on the thickness of the specimen, the intensity that you record or the phase shift that is caused actually is what gives you the contrast in the high resolution micrographs. So, if I summarize all of these and bridge them together, if I look at the imaging system in a transmission electron microscope, the specimen itself has a projected potential, and when the electron beam goes through this, inherently you are introducing a phase shift due to the projected potential, and when this is now modulated by the impulse response function of the microscope system, and if I record the information, what I record in an image is a convolution between the object function, which is inherently a convolution between the projected potential and the lens aberrations, and this convoluted with the impulse response function is what I am recording in an image. And if I look at what I record at the back focal plane, it is related to this information through a Fourier transform, and what I record at the image plane is again an inverse Fourier transform of this. So, from all these you can summarize the information you record for an exit wave is given by a function like this, which is strongly dependent on the thickness, the defocus and the lens aberrations. And by minimizing the spherical aberration and chromatic aberrations, your aberration corrector actually breaks the resolution barrier. This is imaging by looking at parallel illumination, whether it is bright field, dark field or high resolution imaging. Now let us see what happens when you converge the electron beam to a probe and record the information by rastering the electron beam over the specimen and collect the forward scattered electrons on a detector. So this is called as imaging in STEM mode. So you form a probe here, and typically by using special apertures here, you are limiting and restricting the aberrations that are formed on the probe when you converge the beam here, and by choosing only the central beam that is converging to a very sharp point, you raster this onto the specimen and you record the image. The forward scattered electron, like in case of the bright field and the dark field imaging, is scattered through various angles, and if I look at the rastered image from left to right, when you raster, the features that are showing you a difference in the atomic number or the thickness will naturally give you a variation in the contrast, and this image on the left is recorded by collecting the signal which is scattered at a slightly higher angle. And if I look at this from the top view, the configuration is the bright field detector is somewhere at the center where I am collecting the forward scattered information closest to the principal axis, and by using an annular dark field detector I am collecting the radial information which is scattered at a slightly larger angle. And if I understand the contrast mechanism by taking an area integral over this kind of a detector, when the probe interacts with the specimen, your exit wave can be written in terms of the radial coordinates like this. So the specimen modifies the amplitude and the phase locally. The transmission depends on the atomic structure. In a STEM, when the probe position moves, so if this position vector is changing, this is how my position vector changes. And when I look at the measured intensity, the intensity as a function of the position change can be integrated over a solid angle which is recorded onto the detector as a square of this exit wave. So this is what your amplitude is, and when you look at this, for small angles you record the bright field image, and for large angles you record the annular dark field image, and this is how my detector positions are. For very large angles, this intensity that you record is actually proportional to the atomic number to the square root of 3, or it is approximately z square, and this is called as high angle annular dark field image. If you look at the scattering angles in a transmission electron microscope, primarily the bright field and the annular dark field detector is still in the regime where you are recording the diffraction contrast information. You intentionally want to record for very small camera lens and with very large collection angles in such a way that the area integral of this intensity is predominantly dependent on the atomic number, and in this configuration you record what is called as a high angle annular dark field image, and this gives you what is called as Z contrast in STEM mode. So, while you are imaging in STEM mode, by using a high angle annular dark field detector, you can visualize the exact positions of the atoms, and the intensity that you record is now strongly dependent on the atomic number. So, typically the images collected with the elastically scattered beams at higher angles show a strong dependency, and this is an annular dark field image which simply shows you the variation of intensity as a consequence of a change in the atomic number, whereas here this is an HAADF high resolution STEM image that is recorded, and you can see that the atomic number when I take the intensities is proportional to the intensity of the image when I take across this planes is proportional to the atomic number of the atoms that are positioned here. So, this is what you get in a STEM imaging mode. This STEM mode of imaging is extremely interesting and important for analytical studies when you want to relate the raster, and from each of the positions when I collect the analytical signal corresponding to the characteristic X-rays or the forward scattered inelastic electrons as well, and this gives you a wealth of information from a specimen. So, after understanding all of these imaging modes, we have moved on to the example of inelastic signals, and we have seen two cases of recording EDS maps and also some introduction to electron energy loss spectroscopy. If I look at the signals in the conventional TEM again, you have elastic signals and inelastic signals, and inelastic signals are the ones which have lost energy after interaction with the specimen, and from the inelastic signal you are actually getting analytical information from a specimen in a microscope. So, inelastic scattering, how does this happen? When the electron beam hits the specimen, the high energy electron beam must penetrate through the conduction and the valence bands of the specimen, and it interacts with the core electrons, and when a critical amount of energy is transferred to the inner shell, you create a kind of a hole, and there is also the generation of secondary electrons during this process, and as a consequence of this creation of holes, you can have intra-band transitions, and as a consequence of this you can have emission of a characteristic X-ray or an Auger electron. And if I look at the Bohr's model of the atom, this is how the electron shells look like, and from the Rydberg constant and the Bohr's model you can actually exactly calculate what are the energies associated with each of these transitions, and it is strongly dependent on the atomic number. So, for every atom, when you measure the energy of the inelastic event that is associated with each of these transitions, you can get to know what kind of valency, what kind of element is present, and this helps you understand the compositions of a material. So, when you look at this, I have just summarized all of this in the discussion now. So, because of the transformation within the atom, because of the transition within the atom, you actually have emission of characteristic inelastic signal, and by using appropriate detectors you can understand what material is present or what atoms are present inside a specimen. One of them is of course looking at the characteristic X-rays. Characteristic X-rays are often called lines because in the older generation spectrometers you were recording them as lines on photographic plates. Each X-ray line has a specific characteristic energy. Typically this is within the range of 0 to 20 kilo electron volts or 0 to 40 kilo electron volts, And if you look at the area under the peaks of each of these characteristic lines, and if you look at the relative proportions of the equivalent weights that are proportionate to these intensities, you can use this through a simple proportionality relationship, and whether they are coming from which kind of a shell from a specific atom, you can quantify, and this is actually called as quantitative EDS mapping or EDS spot analysis. So, when a group of X-ray lines are originating from a particular shell, you call them as the K family, L family or L family lines, and typically you can quantify from these peaks through what is called as the Cliff-Lorimer equation. So, if A and B are two atoms that are giving me characteristic X-ray lines with intensities IA and IB, this is specifically looking at the area under these peaks, you can relate the equivalent weights proportionate to the area under the intensities that you record, and from these weight fractions you can actually quantify how much amount of which element is present, and this is typically used in the EDS analysis that you do. And talking about the other inelastic processes, we have covered the electron energy loss spectroscopy in particular. You also have the generation of secondary electrons, Auger electrons, electron hole pairs and cathodoluminescence. The interband and intraband transitions, you can actually study them and you can link them to the valence band and conduction band transitions. This is typically the low loss spectra that you record in electron energy loss spectroscopy. You can get the information on the bonding between the atoms, the valency and so on. So, this is a wealth of information that you can record from the process called as electron energy loss spectroscopy. Electron energy loss spectroscopy requires a special kind of construction. In our detailed discussion, we have looked at the construction of what is called as an omega filter, or we have also seen the post column Eels filter, which typically consists of a magnetic prism where you are separating the electrons to different energies, and based on this dispersion you get a wealth of information from a material. So, this is how a typical signal in Eels looks like. I have the zero loss peak and then I have what is called as the core loss spectra, and when you look at the ionization edges, this is what consists of the information that you get from the bonding or the valency from different elements. So, typically this is recorded over a range of 0 to 3000 electron volts, and this covers most of the elements, and typically Eels is extremely sensitive to low atomic weight number materials. You can also measure the thickness of the specimen from the bulk plasmon peaks, and with a very high resolution Eels spectrometer you can also get information on surface plasmons and so on. So, if I look at an example Eels spectrum, this is how it looks like, and if I look at it more closely, here is an ionization edge from aluminum. Bear in mind the strong background intensity is because of the thickness of the specimen, and depending on how I change the dispersion of the spectrometer, I can specifically choose a channel of energy and then get spectra from that particular region. The spectrum you record in Eels is analogous to the spectrum you also record in XPS, but in Eels you also have the local position and the microstructural information as well as the electron energy loss spectrum. So, this makes it a very powerful technique. So, if I give you an example of another ionization edge, this is where you do not have the background subtraction yet, but when I fit in something for the background, I can actually see the oxygen spectra and the manganese spectra, and I can see the ionization edges more clearly, and from the shape of the ionization edges and the width of these ionization edges, I can actually get to know a lot of information about the material. And next, if I place some kind of a window and record the pre-edge and the post-edge spectra, and I only filter these out and record only the information around the specific ionization edge, I can get what is called as energy filtered transmission electron micrographs, and this is how your energy filtered TEM maps look like. And from each specific position, if I record yield spectra like this, I can also get parallel yields recording coupled with STEM. So, this is called as STEM yields, and people call this as either PEELS or STEM yields electron spectral imaging. And with this, with a very good spatial resolution, you can also get the spectral information from each of the pixel where your electron beam is rastering through. So, this is about the analytical signals you get in a transmission electron microscope. And finally, before we move on to the last concept that we learned on aberration correction, we also need to refresh our memory on the damage that is caused by the electron beam. Commonly, you have the radiolysis or the knock-on damage or heating, and in radiolysis, when the incoming electron beam actually causes an ionization of the atom where you are breaking the chemical bond. This is predominantly observed in liquids, ionic samples, and also even biological samples. You have the reaction products as a consequence of electron beam interaction, and you are kind of damaging the specimen. In the next case, which is knock-on damage or sputtering or even displacement damage, what happens is when the momentum of the incoming electron beam is transferred such that it can exceed the binding energy of a crystalline lattice. This is when a complete momentum transfer from the electron beam happens to kick out a nucleus from the crystalline lattice. This is where you have to overcome the threshold of the binding energy, and this is typically a 1 in a million probability, but it still happens more often over repetitive events. Such a damage is called as knock-on damage or sputtering. This is also observed in all kinds of specimens, and it is also dependent on the accelerating voltage. The radiolysis and ionization kind of a damage is more pronounced at slightly lower accelerating voltages, whereas when I go to very high voltages, the knock-on damage is more pronounced. So, you have to have a good balance between the accelerating voltage and the dose that is deposited on your specimen. And another indirect consequence of the electron beam interaction with the specimen is the generation of phonons, which are the lattice vibrations which actually cause heating of the specimen, and this is more pronounced for biological samples and typically in metallic samples which are also good conductors of heat and electricity. This is dissipated and you do not have significant heating, but as a consequence of this you might actually damage polymers or biological specimens, and therefore you are imaging them at very low temperatures or cryo conditions, and this is what you have in beam damage. And finally, we looked at the concept of aberration correction. We defined aberration correction as not some kind of a special rectification of the complete electron lens, but more or less like wavefront engineering, and we drew parallels of aberration correction in optical lenses to the electron lenses, and we looked at the lens aberration function, and we saw the Zernicke expansion of aberrations as polynomials, and how the Scherzer theorem tells you that it is difficult to correct the aberration for round electromagnetic lenses. So, if you look at the aberrations in optical lenses, in an ideal case you would assume that all the rays that propagate through a lens would coincide at a point, and in reality that does not happen. You have the meridional and the sagittal rays which are not converging at a point, and instead they converge at a disc or an ellipsoid. And in an ideal situation, when you have a paraxial approximation, the angles are really small, the rays are close to the axis, so you do not have a radial component, and it is kind of a perfect imaging condition. But if you look at reality, the rays have a finite angle and they do not converge at a single point, and there is a deviation from the ideal Gaussian imaging, and you call this as an aberration. This aberration can be described in terms of what is called as a wavefront error, and that is what we saw. You can expand the aberration of the non-coincidence of the wavefront to a single point in terms of some kind of a polynomial here in terms of the scattering angle and the radial coordinate, and this coefficient is what defines your aberration. And in terms of the scattering angle alpha and the distance from the radial separation, you can have terms such as alpha r square or alpha cube or r cube or alpha square r. All these together constitute the basic aberrations in optical lenses, which are also described as the Seidel aberrations. So, alpha is your aperture angle here and r is the field coordinate, and any complicated wavefront can be built when you give an expansion to this aberration function in terms of the Zernike circle polynomials. If you look at the 5 classic Seidel aberrations, they modulate the wavefront in these kind of forms, and if you look at any classic textbooks on optics, you might have seen these kind of lens distortions or aberrations. You call them as spherical aberration, coma, astigmatism, field curvature and distortion, and each of these can be written in terms of the polynomials. For example, this being alpha cube and astigmatism and coma in terms of alpha square r and alpha r square and so on, and from these you can get to know that correction of aberration is actually modulating the wavefront and compensating for these kind of distortions of the wavefront. In classical optics, you are having very good experience in correcting the curvatures or by using combinations of lenses, and the rectification of optical lens aberrations is done as a standard procedure. But in electron microscopes, there is a serious limitation, that is when you have circular lenses, when you have radial or round electromagnetic lenses, because your Laplace equation of the potential has to be satisfied, and if you solve that, you would see that always you would have a positive CS value, and this is what your Scherzer's theorem states. So, to overcome this, the breakthrough that happened is you have to break this symmetry and introduce some kind of ways to modulate the wavefront by introducing multiple lenses. And in this effort, there were attempts made especially by the groups from CEOs from the University of Ulm and Darmstadt and Jülich, where they worked on the hexapole kind of a construction to minimize the spherical aberration correction, and the group from Arizona State University of Professor Andrei Krivanek and Nick Delby, together they were looking at the octupole quadrupole combination. With this, the idea of stacking electromagnetic lenses telescopically one over the other was thought about, and by minimizing the engineering defects and with the feedback controls, what people have achieved is the breaking of symmetry of the round electromagnetic lenses and the compensation of the field and introduction of a negative CS, because the round electromagnetic lenses always give you a positive CS, and by combination of these hexapole or dipole, hexapole or quadrupole and octupole kind of combinations, you can look at the analogies to the Zernike mode and TEM aberrations, and by engineering the wavefront, you are actually compensating the, or you are balancing out the electromagnetic fields to compensate for the wavefront distortions, and the larger distortion free region you have here, the radial component of this gives you a better resolution. And nowadays with this, people have achieved resolutions as low as even 0.5 angstroms, or even, if I am not wrong, 0.3 angstrom. and we are at the ideal limit of aberrations as on today. So, by correcting spherical and chromatic aberration, we have pushed the boundary of resolution limit in transmission electron microscopes, and this is what you have in most of the modern day microscopes now. Just briefly refreshing your memory on hexapole correction, there are combination of two hexapoles with two transfer doublets in between. The hexapole initially introduces second order and third order distortions and aberration, and the transfer doublet images the first hexapole onto the second with a magnification of -1, and the second hexapole cancels out the second order aberrations, and you are left with only the third order spherical aberration, and this is in a negative value. This negative CS now cancels out the positive CS of the round electromagnetic lens, and this is how you correct for the spherical aberration with a hexapole kind of a corrector. Then when you have the quadrupole octopole corrector, you have a symmetric design where you have a combination of the octopoles and quadrupoles, and even in this, by introducing the double symmetry, you are cancelling out the coma distortions and twofold aberrations. When you do an antisymmetric excitation, you are cancelling unwanted multipole effects, and ultimately with the octopoles you are controlling the third order fields and you are introducing a negative CS again. The advantage of this quadrupole octopole kind of a construction is you can also have crossed electric plus magnetic quadrupoles, and the electric component here acts as a first order Wien filter, and this also acts as something called as a chromatic aberration corrector. So, what happens is, if one of these one of the quadrupoles, if I am replacing with the electric component, for any small distortion in the incoming electron wavefront, if there is any gradient in the energy, the faster moving electrons bend more inward and the slower moving electrons bend more outward, and you are now kind of compensating for the chromatic spread, and with this kind of a construction you can also have chromatic aberration correction as well. So, with this you break the 1 angstrom resolution barrier and you achieve very good resolution, and with the feedback control and the very good electronic stability of these components, it has become more or less a standard practice these days with installations of electron microscopes with both spherical, and there are very few installations of chromatic aberration correction as well, and this quadrupole octopole kind of a corrector is very commonly found for the neon systems, which are exceptional for spectroscopy studies as well. So, with this I hope I have summarized all the lectures and all the concepts that we covered. I am sure this must have been quite loaded, but this will just give you some kind of information on a kind of a flow on the structure of the course and a brief recap on what has been covered. So, with this I will end this discussion here. Thank you, and I hope you find this content useful, and maybe it helps you go one step further and gain better understanding when you are doing microscopy practically. Thank you very much.